Hello everybody, welcome to the Scalable Data Science course. Today's lecture is also on frequent elements and we will do two algorithms today, one on space saving and the other on count min sketch. My name is Anirban and I am a faculty at Computer Science and Engineering, IIT Gandhinagar. So, before we start, just a brief review of the streaming model that we have seen, that we are dealing with only the arrival only streams, and the elements of the stream could be element IDs. We have only really dealt with, examples that I have shown you are really about element IDs, but it could also totally work with the when you have the ID and positive frequency updates, because you could always imagine the positive frequency update as multiple copies of an item that is coming in a stream. Okay. Today we will sort of talk a little bit on about arrival only streams, but then also talk about some data structures that work with arrival plus departure models. Okay. And in last class we did this deterministic we tackled the question of frequency estimation in one pass, right, that given a particular stream that is of length m, we want I should use this word sketch a little carefully, because today we are going to distinguish between what we call a sketch and what is and a little more precisely maybe, right. So, we want a data structure, let us say, and very loosely we are calling it a sketch that can answer frequency queries at the end, which means that if the frequency of a particular item is f(x), I want to return some estimate of it. And this is the kind of guarantee that we got, that if f(x) is the original frequency of an item x, and you have a user defined error parameter epsilon, right, which presumably is something like fairly small, let us say 1% as an example, and then you can return an estimate f hat of x for any item x such that f hat of x lies in this interval. And the amount of space that you need is not even order, it is actually exactly 1 over epsilon times log n, rather 2 over epsilon times log n. Okay. So, let us talk about a very similar algorithm to what we have. Okay. So, if you remember what our Mishra-Gries algorithm was, it looked very much like this, that we keep k counters and items in hand. We initialize by setting all counters to 0, and then when we try to process an item, right, we say that okay, the first two steps are the same. If x is same as any item in hand, of course you increment its counter. If you do not have enough items in hand yet, if the number of items in hand is less than k, of course you store x with the counter 1. But what do you do if you already have k items in hand and x does not match any of them? So, remember what was Mishra-Gries doing? What Mishra-Gries would do is that it would drop x, this copy of x, right, it would drop this item, and then it would decrease the counts of the existing items that you have, right. And this led to this charging argument that we had for giving the guarantee. The space saving algorithm, right, developed by Metwally and others, does something slightly different. What it does is that it does not really throw away x. On the contrary, right, it looks at the item that you have in hand that has the smallest value of the counter. Okay. It throws away that item, replaces that item ID with x, and it increments the counter ID. Seems pretty strange, and we will run through an example, right. But remember what it is doing. So, it is not throwing away, it is not decreasing any any count at all, right. It replaces the smallest counter ID with the ID of x, and it increments the counter. Well, incrementing the counter is intuitive because you are accounting for the arrival of x, right. But it does seem mysterious. Why are we assigning some other items count to that of x? And what happens when you query? Well, that is fairly simple. If the queue is in hand, right, if the algorithm is tracking q at the end, then you return its counter, else you return 0. Okay. So, why is this a useful algorithm? So, first of all, it should also be fairly easy to see that the space that you have is again, that the space that you need is again 2k log n, right, which is fairly, I mean depending on the value of k, this could be fairly nice. So, that is so there is no doubt about that. Okay. Let us run a small example. Suppose we are dealing with k equal to 2. Okay. So, first we track red, count 1, blue, count 1, then we get 2 copies of red. So, okay, this is easy, this becomes 3, then we get a turquoise. Okay. So, now what happens? Now, we drop the blue, we add in a turquoise, then we increment the count of this becomes 2. Now, you get a blue, right, and now again because turquoise is the one with the minimum count, you delete the ID of turquoise, you make it blue and then you increment this to 3. Then we get 2 reds, this becomes 5. Then we get a blue, right. Well, I am already tracking blue, so this becomes a 4. Then we get a turquoise. So, this is still the smallest element, smallest counter. So, this becomes turquoise and this becomes 5. This becomes yellow. Okay. So, now there is a tie, you could do either, let us just do this one. This becomes yellow and this becomes 6, this becomes blue, this becomes blue, this becomes 6. So, it might seem pretty weird because at the end of the stream we are kind of predicting that blue has 6 and that yellow has 6. Well, yellow does not really have 6, but this will be in some error, I mean we will still be able to prove some kind of error bound for this. Okay. But what is the count of blue? 1, 2, 3, 4. So, blue is not so far off, but yellow is really far off, right. And for red we should have our estimate is 0. So, it does look like, is this algorithm any good, right. It is certainly more complicated, looks more complicated than the Mischagres algorithm. So, let us try to analyze it. It turns out that you can give similar guarantees for this algorithm, right. And let us break down the claim that we have into 2 claims, into 2, although claim, I mean claim 2 also will imply claim 1, but let us break it down. Okay. Suppose we say in the first claim and the one that we will actually prove in this particular lecture says that if an item, supposing we set k equal to 1 by epsilon, which means that we are storing 1 by epsilon count item IDs as well as their counters. If the true count of an item, right, which means that if x is such that f x is strictly bigger than epsilon m, right, then we can guarantee that these items such an x is present in hand, right. This is what we will guarantee. Okay. That means that we will track all these heavy hitters. Furthermore, what we will track, what we will say is that consider the estimate f hat of x. So, remember what the estimate f hat of x is, because if an item is being tracked at the end, the estimate is the estimate is f the counter value. If you are not tracking the item, the estimate f hat of x is 0, right. So, the estimate f hat of x will satisfy f hat of x now is at least f of x, and f hat of x is at most f x plus epsilon m. So, now instead of now we have a lower bound by f x and an upper bound by f x plus epsilon m, right. So, at least in the example that you saw, we are getting both the items are satisfying this lower bound, right, and it is fairly easy to see why this should be the case, why f hat of x is bigger than or equal to f x. Okay. So, let us argue for the first claim at least, because even that is not obvious. Okay. So, the trick in analyzing this is in understanding how the minimum counter behaves, because in some sense, I mean if you have noticed in the example, as items move in and out of this set of k, right, the minimum counter acts as the storage. It kind of stores it kind of stores all the updates that have been made to items that were once in the storage and that have moved out. the minimum counter stores that value. Okay. So analyzing that is the critical part. So, here is the first statement, and that is very easy. What we will say is that at the let me call the minimum counter min, right, and let me say that the value of the minimum counter at the end is min. So, what we will say is that this value min is at most epsilon m, it is not that big. Okay. So, why is that the case? So, here is the critical point, that if you sum up all the counters, right, you get m exactly. So, this is very unlike Mishra-Gries, because here we are not doing any deletions, right. So, if a counter, if an element moves out of the set, right, it deposits its value with the minimum counter, right. So, therefore, the total sum of all the counters is still m, and because it is the minimum, the average, because we have 1 over epsilon counters, the average is epsilon m, and therefore, the minimum of these counters is at most epsilon m, right. So, then that seems fairly obvious, this is done. Okay. So, the next is the more tricky statement. What we will say is that suppose consider an uncounted item at the end, right, that is, consider an item that is not present in this list of items that you have at the end, right, let that item be y. So, the algorithm is tracking this list of items, right, and y is not present there. Okay. So, what we can say, what we can claim is that the true count of this uncounted item is within 0 and min. Remember, min is the smallest of these counter values of these items that have been tracked, and this is what we will claim. Okay. So, why is this the case? So, let us imagine the last time y was dropped. So, let us say at step t y was dropped. Okay. So, what does it mean? That means that in the steps from t till m, y never appeared even, right, that in this region, in the interval from t to m, right, y's frequency is 0. Okay. So, because if it had appeared, right, then this, if it had appeared in this interval, then this would not have been the last drop. Okay. So, now consider the value of the min counter at this step. Let me denote by min of t, right. So, it could be, so first of all, it is not hard to see that min of t is less than equal to min, because the value of the min counter always increases, right, it never decreases at least, right, because everybody that is sort of everybody who is leaving deposits itself in the min counter, and so it always completely it always increases. Okay. So, and now because y was dropped at this step, the frequency of y at this step t is less than that of the min counter at this step. So, f of y, which is the frequency until step t, but which is also equal to the total frequency of y, because y does not have any occurrences in the interval t to m. So, therefore, f of y is less than equal to min t, which is less than equal to min, and we have argued that min is less than equal to epsilon m, right, which is something, I mean, but this is a little stronger statement, that the true count of an uncounted item is within 0 and min, right, and therefore, the true count of any uncounted item is less than equal to epsilon m, and therefore, if an item does have a true count bigger than epsilon m, it must be present in hand at the end. Okay. So, this so you need to think about this proof a little bit. Okay. So just do that. Basically, the same proof can be sort of modified a little bit to prove a stronger claim, but we will not do that, because it is a little sort of it is a little complicated. Okay. So, instead what we will do is move to other kinds of data structures, and here is where the definition of sketch comes in, right. See, the data structures that we have looked at until now, this Mishra-Gries, the two algorithms for frequency saving, Mishra-Gries and space saving, these are known as counter based algorithms, right. Because see, what is really happening is that we are sort of adding and dropping counter, I mean adding and deleting element IDs from the set, and we are just keeping counters. So, this is more a matter of nomenclature, but these are not known as sketches, you will find these referred to as counter based algorithms. In practice actually they only really work for arrival only streams, the proofs work only for arrival only streams, but in practice on arrival only streams they are substantially more efficient in terms of space as well as update time than the other set of more general algorithms that we will look at in a little bit. So, if these are not sketches, then what is a sketch? Again informally, a sketch is defined as a compact data structure that allows both inserts and deletes. Okay. So, you should think of it as kind of more having some linearity kind of properties, right, that you can both do updates, you can do different both positive and negative updates to the frequency of an item, right. Then we will call it a sketch. Okay. So, what we will do in these sketches is that we will somehow compute a linear transformation of the input, and I will show you what the we will cast you in this form, in this the algorithms that we see in this form later. And because you can do both positive and negative updates, it naturally works for most of it naturally works for arrival and departure, right. Some of it will need a little bit of modification, but not major modification. Okay. So, the first sketch algorithm that we will consider is known as the count mean sketch, and this was developed by Kormod and Muthukrishnan. So, in order to think about this sketch, again the right way to think about this is to say that okay, we have a frequency. So, think of the input stream as a frequency vector, right. So, think of it as a frequency vector where the dimension is u, right. The elements that have not appeared in the stream have frequency 0, and the elements that have appeared have the frequency f x, right. And then what we are trying to do is that we get this frequency vector not in terms of in terms of only the updates, in terms of only the updates to the frequency vector because we see the element IDs with the frequency implicit sort of update 1, or we see the element ID with the update plus some plus c, right. And the question is that given this stream of updates, can you answer queries about the resulting frequency vector? Okay. So, what count mean sketch does is that it sort of it creates a small summary, and the summary has two parameters. It has a w parameter which has a d parameter. Okay. So, the summary will be of size w times d. There will be w hash functions. Each of them will map each element of the universe to one of d, right. So, the hash function 1 will map each element of the universe from 1 to d, the hash function 2 will map from 1 to d, and so on, right. So, how do we use these hash functions? Okay. So, here is the algorithm. So, in the same sort of framework that we have been writing other streaming algorithms, that first we do the initialization. In initialization we choose h1 to hw, and at this point let us again assume that h1 to hw are chosen uniformly at random, right, that it is a completely random hash function. Again we will I will point out to you that you do not really need completely random hash functions. Something like log 1 over delta independence is fine, or something like that, some constant, some k independence is fine, for some value of k, k universality is fine. And you also initialize this AWD matrix to be all zeros. Okay. Now, what do I do when I get a process x, right? So, I could get the item ID itself or the item ID with some update. You look at each of the hash functions, right, and then you try to see where this particular hash function would put this element. So, you look at the corresponding. So, for 1 you look at 1, this is where hash function 1 says that x should go. So, you update this entry, right. Hash function 2 says that okay, hash function 2 puts the element in this column. So, update this entry. Hash function 3 puts the element in this column. So, you update this entry, and you update each of them exactly by c, right. So, when you query, so what do you do when you query? So, this is interesting, right, because you have w estimates now, one for each of the hash functions. So, you can look at a I h I of x, a 1 h 1 of x, a 2 h 2 of x and a w h w of x, right. All these I mean here w is 3, so all these 3 buckets. What do you do? Well, you could have considered you could have calculated the average, you could have taken the median. The first thing we will analyze is what happens if you take the minimum, right, and why is that an interesting thing to do, okay. And that is where the name count min sketch comes from. Okay. So, let us again run a small example that suppose we have this stream and suppose I have written the hash functions out like this. So, each column represents a hash function. So, h 1 maps blue to position 2. So, let us say this is position 1, this is position 2, this is position 3. So, h 1 maps blue to position 2, yellow to position 1, red to position 1 and blue and turquoise to position 3 and h 2 maps similarly. So, now first we see a red, right. So, if we first see a red, then we get so h 1 maps red to position 1. So, I get 1 here, right. Then I see a blue sorry, and h 2 maps red to position 3. So, I get 1 count out there, right. Then I get a blue, right. So, blue h 1 is mapped to position 2 and h 2 is mapped to position 1. Then I get another red here, here, another red here, here. Then a turquoise is position 3, position 2, position 3 and position 2. Then blue is position 2, position 1, position 2, position 1, red again 3, 1, 3, red 1, 3 and then blue is 2, 1, 2, 1, turquoise is 3, 2, 3, 2, yellow is 1, 2, 1, 2 and then blue is 2, 1, 2 then 1. Okay. So, now the count here is the resulting count here is equal to 6, the resulting count here is equal to 4 and so on, the resulting count here is 4, the resulting count here is 5 and so on. Okay. That is clear. Okay. So, this is the data structure that you will have in the end, this matrix AWD. Right. And suppose we are given the query of the red, right. So, I look at the position 1, I get a count of 6 here and I look at position 3, I get a count of 5 here. So, I return the minimum of 5 and 6, which means that I return 5 on query red. Okay. So, that's how the algorithm works. So, let us analyze this. Why is this good? So first let us analyze the easy things, which is the runtime, the update time and the space. The space clearly is order WD. Times, well, there is a log n, right, because you are keeping so many counters. What is the update time? Well, each hash function updates only one of the positions. Okay. So, therefore, each element does W updates and therefore, the update time is ordered W. So, what are the guarantees? So, let us set W to be 2 by epsilon and let us set D to be log 1 over delta. So, remember what we intuitively want epsilon and delta to be. Epsilon we want the error parameter and delta we want the confidence of being correct, or rather 1 minus delta to be the confidence of being correct, the probability of being correct. Okay. So, delta is error probability. So, now as we mentioned, right, let me we have at the end when we are querying, we really have W estimates. Let me call this y 1 to y w. So, y I is has the content of the cell A h I of x. Okay. So, then the final estimate that we return is really the minimum of these y i's. Okay. And what happens at the minimum? So, consider the arrival only model for now, because we will need to change the algorithm a little bit to consider deletions. So, in the arrival only model, it is not hard to say that each y I is actually bigger than or equal to f of x. Okay. Why is this? Well, it is very easy, because when x comes, every instance of x, you are updating each of the cells a I h I of x. So, therefore, I mean there could be other updates to the cell because of other elements, right, as we saw. So, therefore, each y I is at least f of x, okay. And therefore, the minimum of the y I's is at least f of x, which means that f hat of x is at least f of x. So, that is nice, but what about the upper bound, right? Okay. Let us now calculate what is the expectation of y I. Okay. So, y I is clearly a random variable, and the randomness comes from the choice of the hash function. So, what is the expectation of y I? The expectation of y I is a sum over all y such that map into this particular bucket, that is mapped into this particular bucket by this particular hash function, and the frequencies of these y I's, right, summation over all y I such that h I y equal to h I of x, sum and the sum is and then you sum f y over these y I's. Okay. And it is not hard to say that this expectation is really, I mean x is there in the set, right. So, this expectation is x plus for any other y I, for any other y, what is the chance that it will be what is the chance that it will be mapped to what is the chance that it will be mapped to exactly this bucket, right. Because the size, because it is uniform random hash functions, the chance that any other x, I mean any other y maps into the same bucket of x is really 1 over w, right, which is epsilon by 2, and the total frequency of the of all the other y's is really m minus the frequency of x. So, therefore, the total frequency, the expectation here over all other y's, over all y's not equal to x, is the total frequency times the probability of any one of them mapping into this bucket, right, which gives you epsilon by 2 times m minus f x, right. And this will write simply as f x plus epsilon m by 2. Okay. Okay. So, this is nice. So, now we can apply Markov's inequality, right, because, so consider the random variable y minus f x, right, y I minus f x. So, first of all we say that that this random variable is a non-negative random variable, right, because of our previous argument that y I is always greater than or equal to f x. So, we have a non-negative random variable. What is the expectation of this random variable? Expectation of this random variable is exactly this quantity, right, is exactly this quantity, because it is equal to the expectation of y I minus f x. Okay. So, then we have a random variable, non-negative random variable with this expectation. Therefore, the probability that this random variable will exceed the value epsilon m, right, is expectation divided by epsilon m, which is at most half. So, that is simple algebra. So, therefore, the probability that any one of the y I's crosses f x plus epsilon m is at most half, and we are almost home. Okay. Now, what are we doing? We are taking the minimum of log 1 over delta of such random variables, right. Because we are taking the minimum of log 1 over delta of such random variables, therefore, the chance that the minimum will cross, if the probability of any one of them being bigger than f x plus epsilon m is half. If the minimum crosses f x plus epsilon m, that means that all of them are bigger than f x plus epsilon m, and the probability of that is 2 to the minus log 1 over delta, which is less than delta, right. So, therefore, the probability that the minimum of the yi's crosses f x plus epsilon m is less than delta, and hence with probability 1 minus delta for any query x, f x lies in this interval, f x less than or equal to f at x plus epsilon m. Okay. So, let me go back a little bit, because I might have made I think we made one small mistake. Okay. So, in here, as you might already have noticed, the number of hash functions, we are using w for the number of hash functions, and w is equal to 1 by delta and d is equal to 2 by epsilon. So, the rest of the argument holds as follows, right. The rest of the argument holds as follows, because the probability that h I of y equal to h I of x now is 1 by d, right, which is equal to 2 by epsilon. So, we have just mixed up here the notation between the w and the d, but now that is fixed. Okay. So, just to summarize, in this lecture we looked at two algorithms for frequency estimation. One was counter based, that was space saving, and the other one was sketch based, that was count mean. So, while I did promise you sketch based algorithms that work with both updates and with both additions and deletions, as you might imagine, as you might have noted, the count mean proof does not completely work for deletions, right, and that is because we are taking the minimum, and so we were saying that each yi has to be has to be bigger than or equal to f x, but that will not be true if you are doing deletions, because yi could, because something else might be deleted, and so yi could small less than f x. However, you can easily fix this. You can easily fix this by taking the median instead of the mean, right, and that you should try to work out yourself. If not, you can look at the lecture notes that are pointed to at the end. So, the entire algorithm for CM works. The only thing that you need to change is that you when you are returning the query, when you are answering the query, you take the median of the estimates instead of the minimum. So, a broad guiding principle that I would like to take is that the way you design the sketches is that first you come up with error bounds and confidence estimates, and you use these as design parameters for the data structure. And this principle will come up over and over in the later parts of the course. So, thank you.